So this isn't the video that I wanted to put together for today, but I still think the content's going to be interesting. So I was hoping to focus on string search algorithms, so specifically what's built into C# to do something like an IndexOf for looking for substrings, compared to something like the Aho-Corasick algorithm. I'm not even sure if I'm pronouncing that properly. So unfortunately, what I failed to realize is that it would not be an apples and apples comparison. It's really like apples and oranges, because my implementation of the Aho-Corasick algorithm is really focused on going through binary data and not strings. So with that said, I want to jump over to the code, look at some benchmark setups, and really this is going to be framing for how much better do I need to make my Aho-Corasick algorithm to be comparable to what's built into C# for strings. So here in Visual Studio, I am using benchmark.net. If you're not totally familiar with this, it's a very popular benchmarking framework. There's a NuGet package and everything available for it and tons of examples online. I'm just going to walk through what we have for a setup here. So in the beginning, you can see that I have some parameters. This is just going to be the different combinations of benchmarks that we're able to produce here. So what I'm looking at is comparing the length of the signature or the substring that we want to be looking for. We want to compare different counts of how many signatures we have. So for example, a very simple string index of would just be like one signature, and then the length of that signature, length of the substring in that case, is sort of this second parameter that we have here. The next, this source length, is actually how long that string data is going to be. And then because I have to populate what this content looks like, I'm not really using a variable configuration here for this parameter. I'm actually just using a single 5% sort of frequency that we're coming up with. I figured it might be interesting later to play around with what happens if this is greater or smaller. But for now, I figured I'd keep it pegged at 5% and we'll just see what happens with that. The next part of the code I have on the screen is just some global setup, and what that means is just before each benchmark is run, this code is going to set up the data that we're looking at, and that way we can use the parameters that were defined above, because as it goes through the different iterations, those parameters will be updated for us for the next run. This looks a little bit more complicated than it might need to, only because I am pulling in some of the code from the other project I'm working on. I'm using AutoFact to pull in some of these classes that I'm going to be working with, but I don't really need you to focus on that for now. Let's just talk about some of the other setup that we have. This part here is really just going to set us up with some different signatures that we can go look up. I am using a random class, but I am seeding it with the same number so that between each run we should end up with the same data. Something that I need to call out here, and like I mentioned in the beginning of the video, I'm going to be comparing string index of to go look for substrings, but the Aho-Corasick algorithm that I've written is actually going to operate on binary data. So these signatures here get defined as byte arrays, but I also need those available as strings. Just to try and make it as comparable as possible, I am using a 1252 encoding, which should give us a 1-to-1 byte to character mapping. This next section here is really just so that I can create the random byte array, and then later on I can actually convert that to a string, because as mentioned, I do need to have a string version and a byte array version in order for these benchmarks to be run. Now, this part isn't perfect, as in it's not going to statistically give us a perfect signature frequency in this data. However, I figured it would be as close as possible, and of course, this part is probably not done in an optimal way, but it's not part of the benchmark, and it's fast enough that I don't really care because I can just go run the benchmarks and leave it waiting. In these last three lines, I've already mentioned that on this second part here, I'm converting the bytes to a string, but this line here on 83 and line 85, this is related to the implementation that I have in my main project, and this is going to allow me to create my Aho-Corasick algorithm with the signatures that I want to find, as well as this array data iterator that will go over these bytes to search. In the original project, I am operating on very large files, and this is why I need this interface to be able to work with. So I'm already at a bit of a disadvantage compared to just the built-in string index of, but I wanted to call this out because this is the constraint that I have to work with. If we jump to this implementation, it is a bit of a dummy implementation in that the API here requires that I have an IEnumerable of slices that I can work on, and they're just read-only memory. However, because I just have this byte array that's passed in, I'm going to return it as just a single slice. The actual implementation inside of my project requires that I have to loop over a very large file stream, but in this particular case, that's just not how it's going to operate. So let's go look at the different benchmarks that we have for the string index of. The first one here is going to be one that we're actually doing a sequential lookup of each of the signatures. So all that we're going to be doing is looking for the signature at a particular offset. If we don't find it, we can go move on to the next signature. However, if we do find one, we're just going to increase where we're at by 1 and then see if we can find the next substring. The reason I'm not jumping the entire length of the substring here is just because in theory you could have a substring that is going to overlap with itself. The next benchmark is very similar, except we're going to run this in parallel. So this way, if you look at the entire body here, this is actually going to be almost the exact same. It's really that it's just wrapped in this parallel for each. And finally, the Aho-Corasick implementation here is just calling this search method, and it has this callback where we're going to be operating on the different match, and this return true just says whether or not we should continue or not. So as you can see, it's already a bit of an apples to oranges comparison because it's not truly just a loop here. I do have a callback, and this is going to have some overhead, so that is a bit crappy in comparison. However, like I said, I've changed the goal of this video because I was totally wrong. I was hoping to be able to say, look how fast my Aho-Corasick implementation is, and the reality is, look how slow it is. So instead of focusing on the negative, I now have some targets that I want to work towards. So before jumping over to the benchmarks, I do want to show you a little bit about my Aho-Corasick implementation, but what I'm not going to do is spend a lot of time explaining what the Aho-Corasick algorithm actually does in detail. So the basis of the Aho-Corasick algorithm is going to use trees, as in this tree structure, and in my particular case, I'm going to be using a binary tree. This is a particular type of data structure. It's not quite like a tree as in TREE, but you can go look up more information on this. And essentially, using a tree structure, we're able to create a mapping of the different signatures that we want to look for. And then if I scroll down a little bit to the implementation of the actual lookup, the way that this works is that it will walk through the data and then try to see how much of a particular signature it can match. And the algorithm itself essentially is optimized to be able to step through until it finds a match and then progress from there. So you can go look up plenty of different implementations of the Aho-Corasick algorithm. In fact, this one that I have here is actually just pulled from GitHub. I do want to go look at a different implementation that can use something like a double array for the tree structure, because right now, this particular line right here on 59, even though I'm using a dictionary, this contains key method call is actually quite expensive when I look at where the time is spent. The last thing that I just wanted to mention, especially if you're thinking about the fact that I'm comparing this to a string index of, is that I am using a for each loop here, and then I'm going to be walking through the different slices that we pull out of this for each loop. Now, in my particular benchmark, this is only going to be one iteration because I'm only ever pulling out one slice for the full length of the data. So really, it's just this inner loop that's going to be going over the set of data. The challenge with this, though, even compared to the index of for the string, is that ultimately I do have this callback that I need to invoke, and the overhead associated with that method call plus creating a parameter to pass back is going to be a little bit more expensive than otherwise we would just have in a string index of. So yes, of course, I'm being defensive about why my algorithm is slow, but in hindsight, I think I probably should have realized it's an apples and oranges comparison. So not totally fair, but I think it's still going to be interesting. So with that said, let's go look at some of the data. All right, so first off, I apologize to anyone watching this on mobile. I understand that the numbers are probably hard to see. I did try my best to actually manipulate this data a little bit in Paint, so it's a little bit messy. You can see in the top right, oops, the top left here, but I just did my best to try and pull in as much as I could so I could zoom in for you. Okay, so let's get started looking at what we see here. If we start looking at the benchmarks here, we can see in the first three lines we have the sequential index of, parallel index of, and then Aho-Corasick following that. If we jump over to the mean column, we can see that in the most basic case, we have 10 times as long to go run Aho-Corasick than just the built-in index of. Now, this is pretty terrible in comparison, and I figured, okay, maybe as the amount of signatures that we want to look at, because this is only for one, and maybe given a variable length of those signatures, coupled with how long the actual source is, maybe we would start to see something kind of change up there. So let's keep looking to see if that happens. But one more thing we should double check here is if we look at the amount of memory that we allocate for this, it's interesting that the base index of that we do sequentially is very little, just 32 bytes. The Aho-Corasick one is actually only a little bit more, but the parallel for each is quite a bit more when we compare, especially to this index of that's done sequentially. One final thing to note is that in this most basic case, the actual parallel version is slower than the sequential one. So all kind of interesting in the beginning, but kind of sucks to see that the Aho-Corasick algorithm that I have is that much slower. As we start going down and increasing the source length, so the next sort of 6 lines here are going to be the ones that indicate a longer source. We can see that the Aho-Corasick algorithm actually gets a lot slower. Now, the amount of memory that's used is actually comparable across all of these top benchmarks. However, the Aho-Corasick algorithm definitely slows down. It's now 2 orders of magnitude worse with respect to performance. So this is pretty crappy to see. But again, maybe we'll see a difference as we go from the number of signatures and the length of the signatures. If we progress down a little bit further, what we're noticing is that this length column is changing, and that's the signature length. But if we do a scan across these benchmark numbers, we're seeing that the number of signatures is the same, the length is changing, and then the source length is changing. The mean is always showing us that the Aho-Corasick implementation is 2 orders of magnitude slower across the board. So for me, this is probably the initial thing that caused me to not want to make this video, because I was so excited to show you how fast it was. But again, if I reframe it, this just tells me that I have a lot more performance to try and squeeze out of my algorithm. It's also interesting to note that with one signal signature, we're not getting any additional performance out of the parallel version. And if you think about it, if we go back to the code, we'd see that the parallel part is only over each signature. So because we only have one signature, there isn't actually any benefit to going parallel. It's literally just overhead. That's what we see for one signature. Let's go to the 10 signature case. I'm just going to scroll down a little bit here and try to get it all on screen for you. But if we start with 10 and look across, we can see that the parallel is actually caught up to performance now for the sequential one. It still has more memory used, but if we look at Aho-Corasick in this third line here, especially looking at the mean here, we can see that yes, it's still 2 orders of magnitude slower. Again, if we continue to scan for what's on most of this page, we will see that Aho-Corasick that I have is almost always 2 orders of magnitude slower. It's just awful in comparison, and I was pretty disappointed in that. But as we get a little bit higher, we can start to see, especially right around this range here, for how many is that? That's 1 million in terms of length, and that's 10 signatures that are 16 characters long. We actually see for the first time right here that the parallel version actually starts to beat out the sequential version. Actually, if I scroll up a little bit higher, that's not true. We can see it happening even above here, where the parallel is beating out the sequential. So that's kind of cool that if you think about it, the parallel benefit, as you might expect, is actually definitely measurable. So something interesting to consider is, can I do my Aho-Corasick in parallel? We'll look at that in a future video, because I have done that. I just haven't benchmarked it here. Let's go to the final case where we have 100 signatures, and then we're looking at the different lengths of that. If we're starting at this 4th line down here, this is the first kind of case where we have 100 signatures. Parallel definitely beating out the sequential. Aho-Corasick is 1 order of magnitude slower, and then actually we start to notice if we scan down, we're about 1 order of magnitude slower than the sequential for Aho-Corasick. but the parallel index of is really flying in comparison. Something interesting to be said there about trying to do this stuff in parallel. The amount of memory that we're using, we're not talking very many bytes at all, but what's interesting is if we're watching this rightmost column, we can see that the parallel version is always using more memory for allocations, but the Aho-Corasick compared to the index of is actually quite comparable. We're talking about 100 bytes different, so really not all that much. Alright, so those are definitely some disappointing benchmark results for my algorithm, but that's okay. Like I said at the beginning of this video, I thought it was still worth putting this content together, because instead of trying to compare myself to the string index of and then being disappointed, I can say, hey, look, if string index of can go that fast, why can't mine? So I have done on the side some other improvements to my Aho-Corasick algorithm. I've been benchmarking this kind of stuff in I don't want to say in isolation, that's probably the wrong word. I haven't been benchmarking it in comparison to string index of, but in comparison to itself, so I can see it getting faster. I will make another follow-up video with one more optimization that I've made. I've talked about it a little bit, or hinted at it in this video actually. You'll notice that if you look at the benchmarks I used for index of for string, I had two variations of it. One was parallel, one was not. Why didn't I do that with Aho-Corasick? Well, that's because it will be in the follow-up video to this one. When I have it done, I will link it right here for you. Until then, it will be another placeholder video. Thanks so much for watching, and let's see what the next results show.